Okay, so I'll get started. So please ask questions as you go along. I should get an audio. I see the question from Andrew already, but I'll answer that. I should get an audio beep if you ask a question. I should be able to see the chat. But please, there'll be time for Q&A at the end, but please feel free to ask questions as we go along. So this work, this is actually a talk that I gave at the Cray user group. Well, I didn't really give it the Cray user group. The Cray user group was in Monterey in California in early May, but I couldn't attend because I got COVID 2 days before the start. But I gave it remotely, so there we go. So it goes about performance of parallel I/O on the 5x60 node HPE Cray EX system ARCHER2. So partners in this work are obviously UKR, EPCC, HPE, and the university. This work was also co-funded a bit by Prace because I did some of this work for a parallel I/O course I gave earlier on in the year. So here's an option. You know, ARCHER2 is the latest UK national supercomputer service. It replaces Archer, and we were interested in, we'd done some studies on Archer as to parallel I/O, what the advice to users were. Did that advice translate onto ARCHER2? What parallel I/O advice should we give Archer users for ARCHER2? So I'll see here that just to sort of basically compare the two systems in terms of CPUs. The interesting thing about the difference between Archer and ARCHER2 is they're both about 5,000 nodes. It's clear that the increase in CPU power of modern machines is coming from we had 24 cores per node on Archer, not more than 5 times as many per node on ARCHER2. But here I'm really interested in the disk storage. So on Archer, the technology was called cluster store. On ARCHER2, it's cluster store L300, just more modern. We had 3 file systems. So work 1, work 2, work 3. You'll be put onto a different one of those depending on which project you're in. I'll come back to why we have 3 file systems later. The number of OSDs. This is the number of effectively. It's a bit premature, but the number of disks. Okay. So immediately the big difference here is that on Archer we had 50 disks, 50 OSTs or object storage targets as per file system, whereas on ARCHER2 we have 12. But that sounds like a decrease. In fact, they're a lot faster. So, and the capacity has gone up by a lot. But we will see that the I/O rates have gone up by a lot in principle, because although we have, the big difference here is we have on ARCHER2 we have a fewer number of much faster disks. Now there is also a solid state storage, non-volatile memory storage system, which is cluster store E1000F. We have 1 file system there. It has 20 OSTs, 20 solid state disk units. It has a capacity of 1 petabyte. That is gradually being rolled out for you. I had sort of early user access to that for these trials. Users will be access to that very shortly, or they may already be able to get on. So this is the ARCHER2 service. I actually put this in for the Cray user group talk. Yeah, that's a bunch of us standing in the office at Bayes. I think I'm on there somewhere, but no, I've not made it onto that picture. So the benchmarking has all been done by simple bench I/O, a benchmark called bench I/O that I wrote, building on some work that colleagues Adrian Jackson and Fiona Reed, amongst others, had done under a previous project. It's written in Fortran for historical reasons. But what it does is it takes a large 3D array distributed across a 3D process grid. And that might seem like a very simple use case, but actually it's a lot more complicated than the standard benchmarks you see often, like IOR, which is so and so that's why I use it. And the aim of the benchmark is to measure output to a single shared file. The idea is you want to use MPI, you want to do parallel I/O libraries, here MPI-IO, HDF5 or NetCDF, to produce the same file in serial and in parallel. So, it's a single shared file. If you run the code in serial or run it in parallel, and you get exactly the single file with the same contents in the correct order. Just if you're going to look at this, I actually have 3 separate output directories. That's because we'll see the file system can be configured differently on a per directory basis. So my benchmark marks to 3 writes in by default to 3 different directories, allowing you to configure them separately. I also do file per process, where each, if you're running on 1,000 processes, you'd have 1,000 files. That's really there for comparison. I know it's a parallel I/O pattern that people do use, but it's really not very good, especially on tens or hundreds of thousands of processes, simply because of the post-processing overhead. And I also write a single serial file for comparison, just to get some limits. Now, this produces a surprisingly complicated I/O pattern. Here's an incredibly simple distribution of data. We have a 4x4x4 array on 8 processes in a 2x2x2 grid. So each process, number 0 to 7, has a 2x2x2 grid. But remember, this is written out in the order in serial, and we can argue about it, but imagine that the fastest moving index is this direction. And the data goes 0, 1, 0, 1, and then it goes back 2, 3, 2. The data from an individual process here is split up into a large number of very, very small units distributed in different places in the file. So this is actually quite a hard I/O pattern to do, because a single process is writing data to a very large number of locations in the file, and we'll see in parallel these locations could actually be on different physical disks. A lot of the I/O benchmarks you see just write out in blocks, so it would be a block of red, a block of blue, a block of yellow. That's not realistic, I don't think. So I like this. It gives you surprisingly complicated, even in this almost trivial situation of a 4x4x4 array on 8 processes, you get a relatively complicated I/O distribution. So you can download that and run it if you want. So the file system we have on Archer and Archer 2, and it's come to dominate actually over the past decade or so, is Lustre. And the way Lustre works, it has many disks. Now, strictly, they're called object storage targets, OSTs. To me, they're the smallest user addressable unit. In practice, it's actually multiple disks in a RAID array, but I think of it as a single disk. So we have multiple disks, and the Archer file system had around 50 OSTs. Each Archer file system had around 50 OSTs. The Archer 2 disk file systems have 12, and the NVMe solid state has 20. So these are your OSTs down here, your object storage targets, which I think of as being physical disks. Now, these are also controlled by a single metadata server. We'll see that the files can live on different disks, or a single file can be split across multiple disks. Whereas that information is stored, we have a database. So a single metadata server controls all the OSTs in a file system. And this could clearly become a serial bottleneck because it's shared amongst all users. So what we did on Archer 2 is, rather than have a single file system with 36 OSTs, which might have overloaded the MDS, we have 3 file systems, each with 12 OSTs. And that means you have 3 MDSs, and they're called work 1, work 2, and work 3. And it's a trade-off between having not having a serial bottleneck of an overloaded MDS versus having enough disks in each file system to give you reasonable capacity and bandwidth. Now, Lustre achieves multi-disk parallelism in 2 ways. The way which I like to do, which is relevant for the benchmark, bench.io, is a single file is stored on many OSTs, and Lustre calls this striping. So, and it's not enabled by default. By default, a single file will be stored on a single disk. But you can easily enable striping. Therefore, a file is striped across, say, multiple disks. However, files may be stored on a single OST. So if you write lots of small files, each file may be stored on a single OST, but different files will use different OSTs. So in fact, the 2 ways to benefit from the parallel nature of the file system, what I mean by the parallel nature of the file system is that it has multiple physical disks, is either to have a single large file striped across multiple disks, or to write lots of files, but let Lustre just basically give them to different disks. Both of those approaches do exploit the entire parallelism. But I should have taken a step back and said that, disk speed is very slow now. Sorry, disk speed is quite slow compared to network speed. So disks are, you can think of disks as probably being the limiting. We'll come back to that, but your 0th order approximation idea is that the disks are the limiting the limiting factor in I/O, therefore having many disks is a good thing. So that's two ways to benefit from the parallelism for multiple disks. One is a single file striped across multiple disks, or one is write lots of files and let Lustre allocate them to different OSTs, to different disks. So this is the new slide. So I have a train. I like analogy. So this is my train analogy. I think it works. This is the way I think of the file system. We have an underground train here with 4 carriages, and we have a platform, and then we have 4 exit doors, and everyone's trying to get on the way out. And what you hope happens is you open all the doors on all the carriages. Everyone rushes out, and they efficiently go through all these doors, and they get out very quickly. So these are the ARCHER2 nodes, of which there are about 6,000. The reason I have multiple doors here is you can imagine an ARCHER2 node has 128 processors on it. You could imagine you could have 128 processes writing from each node. Okay, so that's a decision. Do we open one door in each carriage or more than one door? Do we have multiple processes writing per node, or do we have just the one process writing per node? Then this is sort of the network, which kind of mingles things together. But these I think of as the disks. Okay, these exit gates, these exit doors are the disks. So here we have 4 nodes, each with multiple processes writing. Everyone gets out onto the platform, and they're heading for these 4 exit doors, which are the 4 disks. And clearly, you know, what the bottleneck is going to be depends on the relative speed at which people can exit these doors versus the speed at which they can exit these doors. You know, how many doors do you need to have open on the train to saturate a single exit door here? And also, people are milling around on the concourse and possibly traveling between carriages. So there's going to be congestion. Okay, you don't want to overload the thing. But that is my mental model of parallel I/O. People leaving an underground train, multiple carriages, each with multiple doors, heading to multiple exits from the platform. And immediately you can see there are different issues here. For example, if I have a serial exit door and that corresponds to an unstriped file in Lustre speak, the file is only living on one disk, then it doesn't, having lots and lots of doors open on the train isn't a good idea, because the limiting factor is this. You know, we're overloading this single exit door with too many people coming out at once. So that's an I/O pattern we're going to look at. You know, are we limited by the bandwidth of it? You know, what is the relative bandwidth of lots of doors on the train versus a single exit door here? The next thing is a serial train door. What we do is we have only one process. Now, this is the other common I/O pattern that people use. You know, if people want to write a single file but don't use a parallel I/O library, they nominate one process, say rank 0, to gather the data and write. That's like having a serial train door. So people then have to move between carriages. I haven't shown the links here, but this is like messages over the internal ARCHER2 network, and exit this door. And clearly, having multiple disks here is pointless. You know, you're throttled by how quickly people can get from here. Having lots of exit doors open is pointless because this is your limiting factor. So the question here is, what are the bottlenecks? Where are the limiting factors? Reduced train doors, okay? You know, for example, whoops, I originally had 2 train doors open per carriage. Whoops, I've lost my cursor. But imagine that actually a single train door can cope with more people than the exit door. Well, in that case, it's pointless having multiple doors open per train, per carriage, because then you're just producing congestion. So the balance of, you know, the internal I/O bandwidth of the system, potential congestion on the I/O system, and really the bandwidth of the doors on the train versus the number of people that can exit a single door. Remember, these are the nodes, these are the processes, and these are the disks, are things which we need to consider to try and understand the parallel I/O behavior. And it turns out that the limiting factors on Archer and ARCHER2 are very, very different, So what are the bottlenecks? We did a study on Archer a while back, and we did, you could ignore here, I took this from a webinar, which I think my colleague Andy Turner gave. So you can ignore the Cosma. We did, I think Cosma was a machine in Durham. I might be wrong, but that had a GPFS, which is an IBM file system. But ignore that. We're interested here in the green in the blue triangles and the red triangles. That's file per process on Archer and single shared file on Archer. Okay, and you'll see that basically the most important point is that both these modes of I/O, file per process, which is lots of little files across all the disks, and single shared file, which is one file distributed across all the disks, can achieve about the same bandwidth of about 14 gigabytes per second. So we were able to saturate the disks on Archer using either of these I/O methods, and therefore I would have definitely recommended the single shared file. You don't end up with thousands of separate files. But I mean, basically these results were consistent with a single process on Archer being able to write at about 500 megabytes per second, half a gigabyte a second. Okay, so I measured that, and so it turns out that so this is the bandwidth of a single door from the carriage. Okay, now it turns out that actually, if we opened all the doors, each node could write at about 6 gigabytes per second. So actually, each node, each carriage, if we opened lots of doors, could actually chuck people out at massively more than a single door. However, on Archer, this was the best model. Open a single door per carriage, because the bandwidth of a door, the limiting factor were these. The bandwidth of a door was very similar to the bandwidth of a disk. The disks were very slow on Archer. And so the bandwidth of a disk was about 700 megabytes per second. And so actually, it turned out that because of that, you could saturate the I/O bandwidth in both models. And we got about 50% efficiency. You know, if you multiply 500 by how many disks were there, 50 or 700 by, you get about, you should have been expected 30 gigabytes, and we got 15. But so there's about a 50% parallel efficiency loss due to congestion and such like. But it's quite a clear picture on Archer. It was very clear that you could saturate the bandwidth of a single disk with a single process on each node. Therefore, if you had enough nodes or enough files, you could achieve here 15 gigabytes per second, which was nice. So both single shared file and file per process can achieve 15 gigabytes per second when using all the OSTs, which is up in this limit here, above 50 nodes. So the summary, a single process can write at 500 megabytes per second. A single node could write at 6 gigabytes per second, which seems great. So you think I want to have multiple processes writing per node, but actually the single OST can only sustain 700 megabytes per second. And parallel library MPI-IO. Now the reason I concentrate on MPI-IO is that actually most parallel libraries like HDF5 and NetCDF under the hood use MPI-IO. On Archer, MPI-IO assigns a single process to write per stripe. So what MPI-IO would say was here, okay, it would say I have 4 disks, okay. If I write with a single shared file, I should then open 4. I should nominate 4 carriages as the disembarkation carriages, and open 1 door per carriage. That means people on more nodes, people have to funnel in here. People have to come in from all the other carriages, but the internal bandwidth could cope with that. So on Archer, actually MPI-IO assigns a single process to write per stripe. That doesn't seem optimal, as a node can sustain an order of magnitude more. But as I said, a single OST bandwidth is very similar to a single process bandwidth. And MPI-IO can therefore saturate the file system with more nodes than OSTs. So if you have enough nodes, you can saturate all the disks. And we saw we get about a 50% parallel efficiency, which isn't bad. And the HDF5 and NetCDF results I don't show here, but they track MPI-IO because they're layered in that way. NetCDF calls HDF5, which calls MPI-IO. So that was very clear. So I thought it was going to be a clear picture on ARCHER2. So on the ARCHER2 investigation, I said I wrote to three file systems. They're called unstriped, striped, and full striped. And you can set the striping using Lustre file LFS set stripe, and then you set the stripe count. So the way I set up the benchmark is I set the unstriped to a single OST, the stripe to 4 OSTs, and the full stripe you set it to -1, and Lustre picks all the OSTs. So that would be 12 OSTs on the disk file system and 20 on the NVMe solid state system. and I run 10 times and use the maximum I/O rate. I mean, I/O speed can be very variable. You're sharing the I/O infrastructure, the disks, with all the users on your file system and the MDS. So, I mean, I'm doing a theoretical investigation here. So I ran 10 times and used the maximum. There was only about a 10% standard deviation on the disk, although this was very early in the ARCHER2 service, so it wasn't so heavily loaded. There was much less standard deviation on the NVMe because there was no user service there. And I just used standard system software. I didn't play around with it too much. So first of all, I want to try and work out what the, how much, we know we've got all these disks. Can we saturate them? Is it possible to achieve the hardware limitation? Well, I did what I did on ARCHER2, and I wrote a large number of files with file per process, expecting that would just saturate the disk system, because these would be stored everywhere, and I could work out what the maximum bandwidth of the disk system was. And we got that here on ARCHER. It went up, and then we saw the maximum bandwidth of the disk system. The entire file system was about 15 gigabytes per second. On ARCHER2, when I did that, I got half a terabyte per second. On regardless of whether I wrote to the disk or the NVMe, there was some caching going on here. So I did something different. What I did was, there's another configuration I've not told you, is you can actually tell. I said by default Lustre puts all these files on different OSTs. I told it to put every single file on the same OST. So I've got thousands and thousands of processes. 64 nodes is, however many, 10,000 processes, all writing lots of little files to the same disk. I'm trying to work out what is the maximum bandwidth for disk, and we see very, very quickly that on the disk system, I was playing with number of files per node, but basically we get about 10 or 11 gigabytes per second. And on the NVMe, I had to play around with the number of files per node a bit to get this up, but we're getting about over 50. So the important point is here, if I believe this test, I would say that a disk, an OST on ARCHER2 can sustain 10 or 11 gigabytes per second, and a disk, the solid state storage on ARCHER2 can sustain over 50. Now, I got the hardware limits from an HPE colleague, and the hardware numbers are 12 for disk and 55 for NVMe. So, sorry, I got 12 and 55. The hardware limits were 11 and 55. So, I am clearly able to, so I believe these figures, I believe the hardware figures that a single OST on ARCHER can sustain 12 gigabytes per second. And remember that's 25 times, that's over 20 times what we could sustain on ARCHER. So we do have a much smaller number of much faster disks. We have a factor of 4 fewer disks, but they're more than an order of magnitude faster. There was some I needed to restrict the number of files due to contention again, but I'm just trying to saturate. So that gives me immediately gives me a feeling for the limits. So you would therefore guess that the aggregate bandwidth, we need to multiply this by 12, will be well over 100 gigabytes per second for the disk system, and multiply by 20 for the end, over a terabyte per system. So I see a question from Mark, which I didn't notice. There are 300 plus users at one time. What are the side effects? Yeah, so I mean, typically people's I/O comes in bursts, and so as I said, hopefully I answered that. I only saw a 10% variation, deviation on the. Sometimes you hit a bottleneck and things just stall, but yes, you do. Do you store any of the file in the Mendes data? No, I don't. So no, I mean, these files are tens of gigabytes, and I believe that the metadata server just has metadata. I think the metadata server is actually the NVMe solid state storage system for everywhere. I might be wrong there, but I believe that might be true. So I then did MPI-IO, and the default performance was terrible. There were no benefits from parallelism at all. So basically, I wrote on what. So this is saying basically, if I start to use MPI-IO, I would expect to get better bandwidth if I stripe the if I store the file on multiple disks. So this is saying store the file on 1 disk, 2 disks, and 12 disks. When I went to multiple nodes, the performance is just awful. I mean, you're looking at, you know, just terrible. Sorry, there was one figure I mixed off. A single process can only achieve 1 gigabyte per second. So apologies. So that's the important point. The disks themselves are more than magnitude faster, but the bandwidth you can get from a single process is only a factor of 2 more. So I'll come back to bit. So yeah, so yes, that's I'm running a big job. No, Brian's got an interest. Yes, I would like to try several inches of bench.io. Yes, that would be interesting. Yeah, that would. I'm nervous about doing these things because actually, I did manage to almost bring down the Lustre file system with one of these tests. So yeah, that would. You're right. That's something we might want to do after a maintenance session when the machine is free. You're absolutely right. Running multiple instances of the benchmark simultaneously would be a very good test. Yeah, but I don't like doing that during user service because it does mess up other people. Yeah. So clearly there's something wrong with MPI-IO. It's terrible. Okay. So there were 2 approaches. One is HPE told us that what MPI does is, because MPI-IO nominates a small number of writers out of your processes, it has to move all the data to the process that's going to write the data, and it uses MPI collectives, all gather or something to do that. And there's a tuning called X. There's some magic variable we can set, and that makes collectives go faster. Also, unusually on ARCHER2, historically for a Cray machine, we have multiple MPI implementations. At the very lowest level on the network, there are 2 ways to transfer data. One is OFI Open Fabrics, but there's also something called UCX from Mellanox, and so we can switch to that. And again, previously we'd seen better performance for collectives with Mellanox. So out the box, with the default setting for the default MPI, the parallel MPI-IO performance is really bad. However, with a simple setting, okay, so this is what I'm doing here is I'm comparing UCX and OFI with this new tuned setting. Okay? So what you can see is that it really is a module swap. To switch, you do this. You have to, it's in the documentation, but you don't have to recompile. At runtime, you do module swap. You do 2 module swaps and you use it. So it's very simple to play around with, and it should be in the documentation on how to do that. So first of all, you'll see if we have an unstriped file, okay, which are these blue ones here, it doesn't matter how many nodes you run on. This is this situation here. Doesn't matter how many nodes you run on. If you have an unstriped file, you're limited by the, well, yeah, you're limited by the bandwidth at which you can write to the disk. So I get that. But what you do see is that, again, OFI isn't that good. The UCX is much better. The green and the purple are much better than the OFI. So basically, for my studies here, I went to UCX. So let's look at the UCX bandwidth. At a first look, it looks good. You're seeing that basically, if you have a lot of stripes here, 12 stripes here, or 20 on the NVMe, your parallel bandwidth increases almost linearly with the number of nodes. The more writers you have, the more disks you write to. Okay? That looks great. So qualitatively, that looks good. We're getting parallel I/O bandwidth increasing with the number of nodes, which is what you want in parallel computing, and writing to all the disks. However, if you look at the rates, they're terrible. Well, not terrible. They're not very good. You know, we're getting 10 gigabytes per second on 16 nodes here, when we've seen that actually we'd expect to be able to get the file system should be able to cope with over 100. So we're clearly not saturating the file system. And so now, actually, when I did these tests, apologies, I couldn't run on 32 or more nodes. That's why I stuck on 16 with you. That may have gone away with recent updates, but my MPI-IO benchmarks hung on more than on 32 nodes or more. I need to revisit that, but which is why they stop at 16. But that's what we get. So the MPI-IO summary: the parallel results are very disappointing. Change the default stripe size had very little effect. I haven't mentioned this, but basically all these I/O libraries have two modes. One is collective, one is non-collective. You have to use collective. If you use non-collective I/O, which is where each process writes individually, then the I/O performance is truly awful. What you need is collective I/O, or what can happen is the I/O system can nominate a subset of processes to be the writers, aggregate the data, collect it, and do a small number of large writes. Okay. But MPI-IO uses one writer or aggregator per Lustre stripe. So I saw the parallel I/O bandwidth is limited by our 1 GB per second. What I'm trying to say here is that on Archer, having one process writing per stripe was fine, because the parallel bandwidth of one process, sorry, the bandwidth of one process was similar to the bandwidth of one stripe. However, we've seen on ARCHER2, the bandwidth of one stripe of one OST is much more than the 1 GB per second we can get from one process, and that's what's limiting us. So why not ditch ULFI and make UCX the default? For some codes, it's not as good. So it benefits you for codes which do large collectives, large as in large amounts of data, but there seems to be a higher latency. So for point-to-point codes, the performance is slightly less. So that's a good question, but we're sticking with the Cray defaults, the HPE defaults, apparently. I'm showing my age by saying Cray all the time. But it is very easy to switch between the two. You don't even need to recompile. So Archer, we could saturate the Lustre because OST limit was similar to the per process limit. High aggregate bandwidth for a large number of slow OSTs. On Archer2, we have many fewer OSTs, they're much faster, and MPI-IO is not configured for this situation. MPI-IO assumes that writing with one process per node is a reasonable thing to do. And we get similar issues with HDF5 and NetCDF because they're built on top of MPI-IO. Excuse me. So the obvious thing is, well, you know, you've got this, yeah? You've got one, sorry, no, you haven't. You've got this, okay? You've got one train door open per node, and that is not a sensible thing to do because the bandwidth of a single door is much less than this. Why don't we do that? Whoops, that. We have multiple, these aggregators, as MPI-IO calls them. So that looks like the sensible thing to do. Now, luckily, there is a setting which you can say Cray. So it's a really kind of nasty. This is saying for all files. So this is MPI-CH MPI-IO hints is an environment variable. It's saying for all files. Okay, so Mark says, well, numeraries are MPI. So there are actually two subtleties in ARCHER2. A, we have multiple NUMA regions. We have two physical CPUs, each of which has four NUMA regions. But also, we have two network interfaces per node, which I assume each network interface is attached to each of the two CPUs. I played around with the location of the processes. I played around with two processes per node, either both on rank 0 and 1 or rank 0 and 64, and saw no effect. I think the point is that the bandwidth of memory, the bandwidth of internal slingshot network is so much higher than the bandwidth of the disks that you don't see these effects. So I did look at that and I saw no effect on that. I haven't presented that here, but I believe that because the disks are so much slower than memory and and slingshot bandwidth, we don't see that effect. Now, maybe we will if we could actually saturate the disks, but at the moment we're not getting that. This says instead of using one writer per node, use two. Now, I'm always nervous when you set these things that they actually have an effect, because if you type this wrong, if you do MPI-CH MPI hints, you've set an environment variable which isn't recognized, so it will run. So there's a really useful thing. MPI-IO stats equals 1. At runtime, the MPI-IO library prints out useful information like, this is how many aggregators I have, this is where they are. So the problem is, the really nice thing about this setting here is you have one process writing to each disk. That means you don't have to worry about locking any files, because there's only, once you have this situation, you have multiple processes writing to a single disk, and then you have to worry that they're writing to the same file in a single shared file, and you have to lock. So although having multiple writers per node looks like a good thing, the downside is potential locking. Now they've realized that, and there is a setting you can say, trust me, I'm using collective I/O. Two processes will never write to the same piece. So you do Cray CB write lock mode equals 1. Unfortunately, this had very little effect. So basically, when I increase the number, I count now how many I should have here, and I don't have how many processes I wrote. I presume I ran this on 16 nodes, but I don't have that data here. It's in the paper. Increasing the number of aggregators per stripe, which really ought to help things, didn't help. And changing the lock mode helps marginally, okay, but not hugely. I even played around with stripe sizes. Basically, you're still limited. You don't get any benefit. Again, I tried on the NVMe, the solid state. This had some benefit, the lock mode one, but only, it didn't increase the scalability. We're trying to increase the scalability here, and it didn't help. So I'm kind of stumped here. And this is something this study was finished in May. I haven't had a chance to come back and really bottom this out. But so I always tell users, don't do file per process, because you end up with billions of files. And if you have enough nodes, you can saturate the disks. That was true on Archer. On Archer2, it doesn't seem to be true at the moment. Now, I don't quite understand why. The single shared file parallel MPI-IO gets around 10% of the peak performance on the disk, and only 1%, 10 gigabytes per second versus a terabyte per second of NVMe. Even to get that requires UCX MPI, and it's a global change. So if you have a point-to-point communication code that does parallel I/O, switching to UCX may increase your parallel I/O performance, but it may impact your point-to-point performance. We can. So that's a good point. I'll come back to that. MPI-IO was able to saturate Lustre on Archer because we had a large number of slow OSTs, but because we have a small number of fast OSTs on Archer2, the single I/O process or aggregator per stripe or per node is far from optimal. You ought to be able to affect this by changing the locking mode, but this didn't work. And there's a comment, actually, this relaxed locking mode is okay for MPI-IO, but not for NetCDF or HDF5. That's something of a technicality. So further work with HPE to try and address the poor performance and resolve the issue of the UCX translation. That may have gone away. I want to extend MPI-IO to use the Adios2 library. Adios2 is a more modern library, and it ditches this idea of reproducing the serial file. So in Adios2, it appears that its own file format, BP4, and I think there's a BP5 now, actually under the hood uses multiple files. Now, you don't see that because there's metadata above there to make it look like a single file, but actually it writes multiple files under the hood, and that could be beneficial. As I said, Adios BP4, and I think appears adaptive. It has the same concept of aggregators, i.e., but each of these aggregators now writes to its own file. So you may get away with these locking issues, and we have seen through other colleague Paul Bartholomew has done work on a code called X Compact 3D, where he has seen better performance. But it's hard to be quantitative. I'd like to put that in my benchmark. So let's just go to I'll basically go to try and answer okay, that's okay. I've gone the there's quite a few versions of BenchIO flying around. I will stop. So yeah, so Brian says file proposal. So in some sense, what Adios is doing is it's doing file per process at the library level, but it's presenting you, there's metadata on top, which means you don't see that. And so I guess that's what you're seeing. Yes, yeah, you're right. These files get stupidly big. So as long as you have metadata, that means that you can cope with multiple files. That if you ask for an element, I want element 9,9,53 of array X, that the metadata automatically says that must be element 3 of file 95, then yes, you can get the best of both worlds. But if you do it naively and you don't have any metadata or support for that, it does become unmanageable. But you're right. Okay, I mean, yeah, maybe I'm maybe not being completely correct there. I wanted to. I'm trying to. I'm just using a new machine, so I'm going to basically. So this is the GitHub site. I'm going to try and answer the question that Mark asked. So this code's very simple, but if you look at MPI-IO, what it does is it basically it uses file set view. So it does, I don't know if that's your right, but it uses MPI file set view, where it uses the file type, and the file type is basically, it's this one here. Oh, where are we? Here we are, fine. The file type is a 3D subarray. So actually, parallel IO and MPI is quite simple. You say you create a sub. If you're familiar with MPI derived data, you create a subarray which tells the IO system of this big global array. This is the subarray I own, and then you use something called MPI file set view, which tells MPI-IO I only want to write to that part of the file. So I used two data types. My arrays also have halos, so I use another data type to strip the halos. So I have two data types. One is to specify to MPI-IO what parts of the file each process is writing to, and the other is to strip off the halos because my arrays have halos. And in fact, the actual parallel IO is a very, very simple. It's deceptively simple. So yeah, Brian, it would be interesting. Yeah, so I'm maybe living in the past a bit here in terms of, but you're right. It depends on how the downstream application approaches the problem. That's absolutely right. If your solution to multiple files per process is to have a post-processing script which sticks them all back into a single file, I don't believe that is scalable. But if you have a more sophisticated way of doing it, then. The other thing is that I said file per process wasn't scalable, but well, the problem is, so Richard says do manual aggregation. You could, but the problem is that so yes, there's a trade-off here. Do you have one file per node? Sorry, do you have 128 files per node, which file per process, or 64? Yes, you could do that. You could do that. I mean, my guess, what ought to be optimal, in my opinion, is looking at the numbers. I would guess 8 processes per node ought to be the optimum, because 8 processors can write at about 10 gigabytes per second, and that's the OST bandwidth. So 8 processors per node ought to be the sweet spot. But actually, the metadata server is good enough on ARCHER2 that it can cope with a single file per process. It can cope with, I mean, file per process. Yeah. So if you want to do file per process but don't want too many files, you want to do file per 4 processes, file per 16 processes. Exactly. So manual aggregation via MPI gather and write. Yeah, that would be possible to do. In fact, I've experimented here. The way to benchmark that is not to change the code, but to do file per process, but run fewer processes per node. So actually, that would be a useful benchmark for me to do, which I should do, is to do. Yeah, I should do that and find out what the sweet spot is. My guess is 8 processes per node, which turns out to be 1 per NUMA region. That may be a coincidence. Would be the best. But that I should do that. That would be an interesting thing to do. Yeah, an interesting thing to do. Yeah. So no, I mean, as I said, I say that it's like saying, you know, there's caches on processors, and you say, well, your performance is anomalously high because your data fits into cache. You're like, well, that's great. That's exactly what I want. So I was really interested here in very large. No, I don't. There aren't any downsides to memory caching. I don't think. One of the use cases for the NVMe, which in principle has much higher bandwidth, is as a flash, what do you call it, like burst buffer. You know, you could write data to the NVMe quickly, carry on with your life, and let it drain the disk in the background. So there really aren't any downsides. Well, the problem with I say memory caching, it may actually be caching on the various disks. There may be intermediate disks in the OSTs. I don't quite understand the hardware enough. You do notice though, that when these caches are shared between all users. So when you're the only person on the system, you get a lot of disk caching, which benefits you greatly. And then the more people that use it, the less you get, because it's shared amongst all users. So again, yeah, so. Okay, so thanks, Brian, for the comment. That'll be very interesting to look at. And just said several separate. So yes, so I did think that you could basically do, if you could, if you had MPI-IO capability, you could not write one process, one file per process, but one file per communicator possibly. But you would still end up with, in the way I thought about it, you would still end up with multiple files, but fewer. So yes, you could do that. I think the other problems in my mind is that would lead to multiple files. I did think of I thought you could do a clever trick where you could have multiple MPI communicators writing multiple files, but they would be such that you could just concatenate them together at the end. But having mixed that, so one process writing another, yeah. So that will lead to, well, that's undefined in. So is that a comment on? Is that a question? Sorry, Mag, it's an interesting point. I didn't know if it was a comment on what Angela said or if it was a question. What have you said? Yeah, then you'll get file locking, I guess. Simultaneously read and write to a file is going to, yeah, okay, yes, you're absolutely right. That gets, so I deliberately do something very naive, and I've not done even read here. I mean, it's trivial to do read, but yes, once you have mixed access, that becomes much more difficult, because with mixed access you can't do the collective I/O. You know, mixed access means exactly that's exactly the point. You've got one process of writing and one is reading. If you do collective I/O, that is impossible, because all processes are doing the same thing at the same time. And to get performance, at least for these large files, you need collective I/O. With one process reading and one writing, that would be an issue. Yeah, and I suspect the I/O library there would would lock for every access, because it would say, well, I'm not doing collective I/O, so I don't know what everyone else is doing. I'm going to have to lock the file. And once you start locking and unlocking at scale, the whole thing just grinds to a halt. That makes sense. So yeah, I think it could work with multiple. Absolutely, yes, absolutely, yes. So I should know, but I believe that the Lustre doesn't lock per file; it locks per stripe. I think, I believe so. Just because two processes are reading and writing to the same file doesn't mean they will be locking, because they might be right. But the problem is that Lustre doesn't know that, I guess. So it has to, I don't know. I don't. That's something I need to. I'm not really I don't know much about file systems at their implementation level. I have this very naive view of underground trains and platforms and doors. That's about the level of my, which was a fantastic analogy on Archer. So I think it's a useful analogy. It is a useful analogy. Yes, you're right. Multiple files, it could work. Yeah. Okay, I'll stop sharing. You don't want to look at a website. So I hope you find that useful. And so the talk and the recording will go up shortly. And I saw actually that, yes, so Juan pointed out very timely that people quite rightly asked, you know, if you get better performance with UCX than your OFI, why isn't it the default? Well, it's horses for courses. And my colleague Andy Turner has done has taken a bunch of common applications and done this. And so he will be talking next week and looking at the pros and cons. I think the issue is that it's the plus side, it's a really easy change to make. You know, you just you even not compile time. It's just at runtime in your Slurm script, load two modules. It's in the documentation, and Juan's giving you them there, and you can try them out. The downside is it's a global change, so you may gain in one part and lose in another. But Andy did a whole application study on big applications to see what the benefit, what the various and my naive, from a I have an equally naive benchmark which just does 3D halo swaps, and my naive was that for programs that do very collectors, when I say large collectors, not large in the process, but large in terms of amount of data, which are doing collective operations with lots of data, like parallel FFTs. That's a classic example. You do an all-to-all. UCX is typically better, but for point-to-point communication, OFI is typically better. Yeah, but Andy has more quantitative results than that. Okay, thanks everyone. So yes, different. I did. I have data. I may not even made it into the paper, but I really found. Well, okay. Let's see. Let's just. I'm happy to look at that if I can find the. Slight issue because I have just changed machine, and so I don't have immediate access necessarily to everything that I basically I do have data for that. Sorry, I don't. I mean, it's yeah, sorry, but basically for very small, i.e., hundreds of kilobytes, or very large, you know, hundreds of megabytes. But there was a large spot in the middle from like I think it was like maybe a quarter of a megabyte up to 10 megabytes or something like that. Where for my very large data sets, at least, it made very little difference. It was basically it was you couldn't really tell. So it seems, other than the extremes, clearly a really big one, a really small one, what didn't seem worth tweaking. And the default seemed to be in the sweet spot. And that is for single shared file. That is, one very large file. But that was I did an investigation, and that was my That was my conclusion. Again, that might change if you were actually able to really hammer the disk system. Yeah, this all has to be caveated with we're not hammering the disk system because our bottlenecks are elsewhere. So that will be worth, if we do get some kind of fix to MPI, or able to configure it better, where we can saturate the disks, the hardware limits of the disks, then maybe these things become significant. But at the moment, they're way down the chain in terms of importance. Okay, so that's great. Thanks very much, and hope you enjoy. Well, I was going to say good weather. It's raining here. Okay. It's raining here. It hasn't rained for 2 or 3 weeks, but I better run out and bring back the cushions in from them. Okay. Nice to speak to you, and I hope you enjoyed the talk, and keep an eye out for other seminars such as Andy's next week.